All right, today is going to be, generally speaking, a pretty abstract day, focusing on abstract definitions, theorems, and some proofs. So we'll review the basic definitions and properties that we talked about last time, introduce new definitions and properties of groups. Talk about something in chapter 3, the beginning of chapter 3, the order of a group, the order of an element, subgroups. And if we have time, and I do want to make time for this, when I try to answer this question, what's really going on in modular arithmetic, you'll notice on the homework that I handed back, I didn't grade number 7. Partially that was because I was crunched for time, but partially it was because I realized as I was looking through your homework assignments that I had forgotten to tell you something kind of subtle to do with that problem. So you should, I would like to address that if we have time, and I'll try to do my best to make time for that at the end. Okay? Before we get into it, though, I want to ask a couple meta questions you might be wondering about. For example, what's the purpose of abstraction in mathematics? Do you think if we're doing really abstract stuff here, do you think you could give a purpose for it besides just to get a math major so you can get out? Think of any purposes for it? Hard to think of purposes at 7:40 in the morning. Over here, can you think of any purposes? Learning how to think, I mean, you could talk about purposes for yourself, right? Learning how to think logically. I'm talking about purposes for mathematics, and I can think of 3 big ones. Unity. Seemingly different subjects are actually related. Talking about group theories, there's lots of examples of groups. Okay, so these different subjects, whether you'll be talking about numbers, number system, modular arithmetic, matrices, groups of matrices, groups of functions, they're actually related to each other. So that's it's a unifying thing. And related to that is efficiency. Once you prove something in an abstract axiomatic framework, it is proved for all examples that fit that framework. If we prove some things about abstract groups, like the left-cancellation law, for example, that's true for all examples of groups. So it's efficient, too. Another big one is clarity. This is somewhat my opinion. You may disagree with me. Once you get used to the abstraction, it can actually make things easier. I personally find abstract stuff to be easier than real life stuff because, well, I got used to the abstraction for one thing. I know it's hard at first, it's hard to get used to, but secondly, the real world, applied math is much more messy, you might say, much more unclear about what to do, how to create your mathematical models that describe the world. The world is a very, kind of random place, it seems. We can try to model that in various ways. There is structure to it still that we can praise God for again. But abstract stuff, I think, is actually a little bit more clear because it's just, once you get used to it, it's just, sort of following your nose. What's the next logical step? Sometimes you have to experiment with things, of course, but it can actually make things more clear. Can abstraction go too far? Well, that's a matter of opinion. Perhaps. I will say that even within the mathematical community, there are certain subjects that are so abstract that mathematicians even pejoratively refer to those subjects as abstract nonsense. Both of these are Wikipedia pages here. There's actually a Wikipedia page about abstract nonsense. And it is talking about, in math, terms used by mathematicians to describe abstract methods, especially in something called, here's the big one actually, category theory, which is related to this other one, homological algebra. Category theory was the other link in there. If you ever are interested in learning about category theory, just realize it's very, very abstract. It's basically just about a bunch of diagrams, which in many situations refer to sets and functions, but You talk about it in a real abstract way. However, it does provide unity, efficiency, and clarity, even though it is very abstract. It still has those benefits. All right, so you ready to do a bunch of definitions and theorem statements? And in fact, with this first one, I wrote this on the board last time, but I want to be a little bit more careful this time. I very well could put this on the first exam. What is the definition of a group? Okay? Let's write it out carefully. I've said things verbally, listing off properties. I wrote down the properties in the last lecture. Here I want to be more careful and really state it as a true definition. I'm not looking at the book, so I'm probably not going to get it word for word the same as the book. That's okay, as long as it has the same meaning. So when you write the definitions and theorem statements on exams, you don't necessarily have to get them word for word, but it does have to have the same meaning. Okay? A set G is a group if there is a binary operation defined on G satisfying certain properties. You don't have to add the word closure there next to binary operation because, as I've emphasized pretty much every day, in our book, binary operation implies closure. In general, that's actually not true. Not all mathematicians take binary operation to imply closure. They would just mean it's a way of combining two things to get a new thing. You wouldn't have to add the word closure in parentheses here, but I will. But that would be assumed. It would be okay for you to just say binary operation. Define MG satisfying three properties after that point. The associative law, so you could write AB in parentheses times C equals A times BC in parentheses, and it is assumed in this notation that the output of the binary operation is putting the letters next to each other that represent the group elements. That's assumed. You should add for all A, B, and C and G. That does need to be there for full credit. So make sure you pay attention to those kinds of details. Secondly, there's the existence of an identity. There exists an element that we typically call E in capital G, such that AE equals EA equals A for all A in G. And thirdly, you should put the for all first now. For all elements A of G, there exists an inverse, which we do denote by A with a -1 power. There exists an element A inverse of G in G, such that A times A inverse equals A inverse times A equals the identity. Okay, so there's your definition of a group. Looking over this, I'd give myself full credit, okay? Even if I didn't put the word closure there, because that's going to be assumed for us. Though it does need to be checked in certain examples, like I mentioned last time. Is a property that the identity element is unique. We saw that last time. I won't take the time to write that down. We've got a lot to go over today, so I don't want to get bogged down in writing down too many things. If there were another identity, well, I can write down the essential equations. Call it E prime. You could say that's true. E prime being in identity would mean this is true. And E being an identity would mean this is true. So in fact, E must equal E, right? Left and right cancellation laws. AB equaling AC implies B equals C. And BA equaling CA implies B equals C. Is it okay to put the slashes through the A's to emphasize the canceling? It's not a real big deal. But don't do this. Don't write something like this. That's bad. Don't write it like you're dividing by A. The reason that's bad is because of the fact that not all groups are abelian. Not all groups are commutative. And by writing dividing by A there, you're sort of saying, well, maybe it doesn't matter which side I multiply by A inverse on, because this kind of notation is symmetric. It's not clear. Are you multiplying by A inverse on the left or on the right? So don't write that. Write this kind of thing instead. If you are going to left multiply by A inverse. Okay? Don't write fractions with groups, unless it happens to be the group of rationals under addition, for example. I mentioned, technically speaking, last time, left and right multiplication on both sides of an equation preserves equality. Should be proved. Well, it's a very trivial proof. If you've got two elements equaling each other, so they're really the same element, then if you multiply both sides on the left, say, by A, the resulting thing is going to be equal. Does that really take proof? Well, yes, but it's really just based on the fact that the definition of a function and the fact that binary operations are functions. The binary operation is a function. That's what we're doing when we multiply. We're doing a binary operation. And so we know with functions that for every input there's a unique output. And so A, B is the unique output I get by under the binary operation that maps the ordered pair AB to the point in G, AB. And so if I got the same ordered pair, if these are equal ordered pairs, then they're equal inputs, and they got to get mapped to the same thing. Because functions have the property that for every input there's a unique output. AC would have to be the same thing, because these are the same, because B and C are the same. Okay, so it's a very trivial thing, and the author doesn't even bother mentioning it. Okay, here's some new things. Uniqueness of identities. Let G be a group. Let A be in G. A is an arbitrary element of G. Then, oh, typo, sorry. Uniqueness of inverses. Then the inverse of A is unique. Proof? Suppose I'll call them A prime and A double prime. No derivatives here, right? These are not derivatives. Are inverses of A. Then A prime equals the identity, but so does A times A double prime. By the left cancellation law, then, A prime must equal A double prime. I can multiply both sides of this equation of this equaling this on the left by A inverse, which would be another identity, and that would imply A prime equals A double prime. I can just say it's the left cancellation law. By the left cancellation law. So in fact, there must be just one inverse. It must be unique. You can solve linear equations like this for the unknown x. If you treat x as an unknown, a and b is given. This is just like in linear algebra with matrices. Except, you've got to be careful in that analogy. Oftentimes in linear algebra, A is a matrix, and x and b are vectors. That's the most common thing to do with linear algebra, which is not what we're doing here because we're only dealing with elements from the same group. So the analogy in linear algebra would be that A, x, and b would all have to be matrices. How do you solve that equation for x if A and b are given and x is unknown? Multiply both sides on the left by A inverse. Then you can use associativity to say x must be A inverse times b. Actually, that does not prove that that is a solution. It just implies that's the only possible solution. The logic here is I'm kind of assuming x is an element that satisfies this, and that would imply x would have to equal this. This is the only possible solution. To truly prove it as a solution, though, you really do need to substitute it in place of the x, but it's easy. It does solve the equation. That line does check that it is a solution. It's really the logical proof that it is a solution. And we can write the equation the other way around. XA equals B, and the solution will not necessarily be the same because we're not assuming commutativity. Now right multiply by A inverse. Instead of left multiplying by A inverse. And these two things are different group elements in general, unless the group happens to be Abelian. They could happen to be the same even if the group is not Abelian, but in general they won't. And again, this logic only implies that this is the only possible solution. Technically speaking, you need to do something like this to truly prove it is a solution. But again, it's easy. You can define integer powers of a group element, sometimes called integral powers, but again, no calculus. I'll try to say integer powers. And you make use of the associative property for that. For example, what should A cubed mean? Well, you might say initially it should be A times A times A. But wait a minute. Which product should you do first? Well, because of the associative law, it doesn't matter. This equals this, and it equals this. And these are the same because of the associative law. Therefore, we can unambiguously define that. In general, if n is a positive integer, a natural number, sometimes positive integers are also denoted the set as z plus positive integers. Then a to the n would be a times itself, n times. There would be n factors here. And again, because of the associative law, you can write it like this. Technically speaking, that should be proved with induction, but it's not a real pleasant proof, so I think we'll leave that. How about if n is a negative integer? I don't really typically see this notation, z minus, but I suppose we can use it for the negative integers. Well, a to the negative 1 is just the inverse of a. What should a to the negative 2 be? Got a guess? Had a good definition of that?
Inverse times inverse?
Yep, you could do that. Essentially, you're saying do a inverse squared. You could also do the inverse of a squared. But wait a minute, are those really equal to each other? That should be verified. Does a inverse squared equal the inverse of a squared? Really, if I multiply this thing by this thing, do I get the identity? That's the real issue, right? And when I multiply this whole thing by this thing inside the parentheses, if I get the identity, then the inverse of this thing inside the parentheses must be this whole thing. Got to understand what the issue is. So do that multiplication. A inverse squared times a squared. But a inverse squared is a inverse times a inverse, and a squared is a times a. Yes, this does give the identity. Likewise, in general here, okay, maybe I should think of n as a positive integer and write a to the negative n. That might get less confusing. Negative n is going to be a negative integer then. You could either define it to be the nth power of a inverse, or the inverse of a to the nth power. Though again, you'd have to verify that these really give you the same thing, and you can do that. They do give the same thing. Do properties of exponents hold? I forgot to put that on the PowerPoint. Properties of exponents, does that hold? Does, for example, a to the n times a to the m equal a to the n plus m? Certainly it does in the case where n and m are both positive integers. In that case. Because a to the n is a times itself with n factors. A to the m is a times itself with m factors. Altogether, you'd have n plus m factors. But what about if one or both of them is negative? Let's just think about an example. does a to the negative 3 times a to the positive 5 equal a squared? You got to use what a to the negative 3 means. Use one of these to see if that's the case. Is there one that's easier than the other? I'm thinking, well, you could use either. Let's go ahead and use this one. Technically speaking, you should probably write it out if you're thinking about it for the first time at least. Those combine to give E, making this the case. Then these combine to give E, making that equal to this. I forgot an A inverse here. Then these combine to give E, leaving you with A times A, leaving you with A squared. And you can verify it in general too. What do you think A to the 0 should be? 1, which is really E, yeah. Not 2.71828. The identity. Which is 1 with multiplicative groups of numbers. It's the same as the number 1. Something called the socks-shoes property. Anybody remember from the reading what that was about? Let me demonstrate it for you. My socks and shoes are on. Oh, my hip there. I guess I shouldn't go up so high. My socks and shoes are both on. Let me take them both off. Oh, really? I have to take my shoes off, then my socks off. Okay, I'll put it quickly back on. To put them back on, I have to put my socks on, then my shoes on. How is this related to group theory?
Order of operations.
Yeah, it's related to order of operations. If A is taking socks off, and B is taking shoes off, and then the product AB, maybe thinking of it as function composition, so work from right to left, represents first taking your shoes off, then taking your socks off. Taking them both off. How do you put them back on? AB inverse would be putting both back on. How do you do that? You got to apply A inverse first, and then B inverse, working from right to left. The inverse of AB equals B inverse times A inverse. You have to switch the A and the B around, the opposite order in general. How do you verify that? If this was a proof on the exam, by the way, you should not just write equations, you should write sentences. Multiply AB times B inverse A inverse. Use the associative property. Technically, we should check the other direction as well. But it's basically the same kind of steps. Therefore, the inverse of the element A times B is the element B inverse times A inverse, because these products equal the identity. There are extensions of this. I guess if you got three things, you'd probably call it like the undershirt, shirt, coat property. The inverse of A times B times C is the product of their inverses in the reverse order. C inverse, B inverse, A inverse, etc. In general, we are talking about here. Of course, if the group is abelian, commutative, then you can put these in any order that you want. So again, not all groups are abelian, but some are. Some of the most important ones are. You could say a definition here is, we say, or let G be a group we say G is an abelian group if A times B equals B times A for all A comma B in G. If every element commutes with every other element. Commutative property is satisfied. Before I go on, I should also mention that in general, the nth power of A times B is not equal to A to the n times B to the n. Though it would be if G is abelian. Get equality if G is abelian. And again, realize that when I say in general this is not equal to that in non-abelian groups. There still could be some A's and B's that do commute with each other, even within a non-abelian group. And so this could be equal for some of the elements in the non-abelian group. In particular, if either A or B is the identity, it works. Because the identity commutes with everything. Because of the definition we have of the identity, Lactose definition of group. Special basic properties for abelian groups. Essentially, I'm getting at this, but we will see some others. And you could say, also, here's an example of another one. The inverse of AB is A inverse B inverse if G is abelian. Book talks about additive notation, and this is going to come up on completion problems too. I don't really want to talk much about additive notation. I mean, it's going to come out when we're talking about Zn. We will use additive notation. Essentially, AB becomes A plus B. And A inverse is denoted by the opposite of A. It's okay if you say negative A, but in general, I'll try to say the opposite of A. I guess one more thing worth mentioning is that A to the n power corresponds to n times A, but here you need to realize this is an integer, and this is not necessarily an integer. What this really means is A added to itself n times. N terms here. I will say, I don't think this is mentioned in the book, that usually when you use additive notation, you actually also assume the group is Abelian. But that, we won't make a big deal out of that. All right, it's quiz time.